Okay, so so hello and welcome to one other TA session. So this is Algebra 1 course offered by NPTEL, and I am Shubhajit Dash, one of the TAs for this course. So welcome to week 8. So as we keep doing every week, we'll be solving some exercises and or problems, and those are from the previous year assignment. And I do hope that you are attending Harish's session. So he solves part of the problems and I solve the rest. So yeah, so this week you studied modules, right, Shalini?
Yes, sir.
Yeah, okay. So that's a very interesting, modules are very interesting objects, and sort of they are one of the, I mean, one primary reason for studying modules is because you want to study rings. So you know that a module, what is a module? It's just an abelian group, right? Together with some ring action, right? A ring acts on this abelian group in a nice way. The action is linear and all that. So basically, just as to understand groups, we study actions of groups on sets. To study rings, we sort of study actions of rings on abelian groups. Now, one of the reasons for studying actions is because you want to sort of represent. Let's say you are talking about a group action, and you want to represent the group by seeing it in some concrete form, right? So that is why you study representations of actions of a group, right? Similarly, for rings, you study ring actions so as to understand rings better. Now, a group can act on sets, but for rings, it's always better to have an abelian group, right? Because essentially, what you want to do is see the ring inside some concrete ring, right? Now, if you take just a set, then there is no canonical way of forming a ring out of that set. You need one extra operation on that set, which is the reason rings act on abelian groups and not just sets. So anyways, so whenever rings act on abelian groups, what you get is a module. So a module is an abelian group together with a scalar multiplication by ring elements, right? Okay, fine. So let's start solving the problems. So let's read out the first question. Yeah, so you are taking a linear transformation of R2 into R2, which is precisely clockwise rotation about the origin by pi radians. Okay, so we readily know what the matrix is, right? So we'll get to this, but anyways, so observe that the pair R2 comma T actually defines a left Rx module structure on R2. I'll explain this in a minute. Maybe it was explained to you uh, during the lectures, but anyways, we'll get there. So anyways, we want to find, so basically R2 has now become, R2 which was previously just a vector space over R has actually now become a module over Rx. Rx is a polynomial ring over R. So R2 becomes a module over Rx, and we are asked to find how many submodules does this module have. Okay, so before we start, we do something general. Okay, I think this was discussed, but still let me just go through it once. So let's talk about something general. So let V be a F vector space, and T mapping V into V be a linear endomorphism, that is be a linear endomorphism of V. So yeah, so what we want essentially is, we have V as a vector space over F, we want to make it into a module over Fx, right? So so observe that V is already an abelian group, so consider the ring action. So you have a mapping of Fx cross V into V, right? We want to make Fx act on V, right? So what map should we take? What map can we take here?
Some fx comma alpha would be mapped to alpha dot fx.
Okay, so what is alpha dot fx, by the way? Does that make sense? Because alpha is a vector, but if, what do you mean by fx acting on alpha? If fx would had been a scalar, then we could make sense of this, right? Because fx is in the base field and v already has a vector space structured over it, right?
Yes, sir.
So what do you think? What can we do here? We have taken something more, not just a vector space. We have actually taken an endomorphism of v, right? Can we not use it? We have taken a linear map from v to v. Can we not use it? So observe that if fx is a polynomial in capital Fx and t is an endomorphism, then we can make sense of f of t, right? So let's say, let me give you an example of this. So suppose you consider this polynomial x square, 2x square minus x plus 1 plus 2, let's say, or let's say 3. Consider this in fx, okay? So let's call this f of x. Can we not talk about f of t, which is equal to 2t square minus t plus 3 into identity, right? You need to place a I here because we are talking about operators or mappings here, right? We're talking about maps or morphisms here. So f of t, my question is, don't you think that f of t perfectly makes sense and f of t is a linear map from v to v?
Yes, sir.
It is, right? All of this is happening because if you just take any vector space v and if you look at all the linear maps from v to v, that is, if you look at all the endomorphisms of v, then this has a structure of a vector space over the base field f, but something more is true here, right? It actually is also a ring under composition, right? Addition and composition. So t square,
Yes, sir.
so t square here precisely means that t composed with t. Any power of t means that you are composing t with itself that many times. So E of v is actually a ring that is also a vector space, and you can check that the two structures are compatible in a nice way. What I mean to say is the endomorphisms of this vector space v actually is an algebra over f. Anyways, so we can work with f of t. F of t is a perfectly defined linear map, right? Even though it seems it can't be linear because there's t square and all that, but t square is just composition with t, and you know composition of linear transformations, addition of linear transformations, multiplication of a linear transformation by a scalar, etc., always gives you a linear transformation. So the overall point of this is that f of t can be made, f of t is actually a linear transformation from v to v, and now we actually have our map or action. So you take any fx as you said, and you take alpha and you map this onto, where should I map this onto? So I can talk about f of t, right? But this is a map from v to v, but I want an element of v. So what should I apply f of t on? I should apply it on alpha, right? Because we are given alpha also. We need to use that, right? Doesn't this make sense? F of t is a linear map from v to v, and alpha is here, so you can just take its image under f of t, right? F of t acting on alpha, right? Is it okay?
Yes, sir.
Okay. So this is our action, and you can check that this is a ring action. So just check that v check that this makes, I mean this action along with the additive structure of v, this makes v into an fx module, right? So it's as easy as that. Now let me ask you something. So what we are actually interested in is basically what are the subspaces of, I mean what are the submodules of v, right? So you know what a submodule of a module is, right? It is a subset of that module which itself forms a module in its own right under the restricted operations, right? That is what a submodule is. So we want to find out what are the submodules of v. What are the submodules of this fx module v? Okay. So what I want to say is that you can check. Let me just okay. So let's look at it like this. So if w is a submodule not just a subspace, not just an F subspace, but actually an Fx submodule. If W is a submodule of V, then we know that W is closed under scalar multiplication by the ring elements, right? That is by scalar multiplication by polynomials, right? So in particular, W is closed under the action of X, right? The polynomial X. Then X dot W must be contained in W, right? And what is X dot W? What is the action of X? What does X do to a vector alpha? By our very definition, if f of X maps, or if f of X when multiplied with alpha gives you f of t of alpha, then X times alpha should give you t acting on alpha, right? That's the very definition, right? You just replace
Yes,
X
sir.
by t, yeah. So this implies that X dot W is in W, implies t of W is also in W, right? So this means T of W is actually inside W. So we know that if W is a submodule of V, then T of W is contained in W. In other words, W is a submodule of V implies that W is an invariant subspace of the operator T, right? And conversely, T of W is contained in W just translates to saying that X dot W is contained in W, which implies, and if X acting on W is contained in W, since W is a subspace, I mean it's a, W, uh, what should I say? Yeah, I should say something here, right? Yeah, so I should say it like this. Conversely, if W is a subspace, subspace of V means it's a part of the vector space V over F. Subspace of V over F, then T of W is contained in W. That is, it's an invariant subspace of the operator T. This will imply that X dot W is contained in W by our very definition. And if X dot W is contained in W, then any polynomial acting on W will basically map it into W, right? Because every polynomial is just an expression in terms of X, right? By multiplications and scalar multiplication and all that, right? So
Yes, sir.
yeah. So what I mean to say is it will follow from all this that W is a submodule of V over Fx. Yeah, I mean we didn't need to write this here actually. Yeah. So T of W is contained in W means that every polynomial in T, in the linear map T, will actually map W into W, which means that W is basically closed under scalar multiplication by your polynomials Fx, right? Which means that W is actually a submodule. And note that, so we basically have maps in two directions, right? Firstly, so we have sort of roughly speaking, or maybe precisely speaking only, we have maps. So we have two opposite direction maps. One is from this set, invariant subspaces. Invariant subspaces. Subspace and submodule are different. Subspace means we are talking over F, and whenever we are saying a submodule, we are actually referring to Fx here as our base ring. So invariant subspaces of T, right? And on the other hand, we have submodules of V over Fx, right? So we have a map from this to this, right? What is that map? You take a subspace W and you map it onto itself, right? If W is an invariant subspace of T, then automatically W is a submodule of V over Fx, right? We have seen this, and we have a map in the opposite direction as well, right? Which is submodules of V over Fx gets mapped onto invariant subspace of T. I mean, if W is a submodule of V over Fx, then automatically W is an invariant subspace of T. Now I could also write equality here, okay? It's not a very, I mean, the two sets are in fact equal. They're the same things, we can say. These maps sort of are the identity maps. W on the left is mapped onto the W on the right via the upper mapping, and the lower mapping from the right set to the left set actually maps W1 to W only. But since I am talking about subspaces and submodules here, which are sort of, even though the sets involved are the same here, but the structures are sort of different, that is why I am using mappings here. Okay, anyways, you can also call this, maybe let's say by abuse of notation or something, identity and identity. So my point is that the submodules of V over Fx are precisely the invariant subspaces of T, right? So whenever we are asked to find what are the submodules of some Fx module, we can just look at what are the invariant subspaces of T. And that is what we are going to do for this question. So what is our T here? T is from R2 to R2, it's just clockwise rotation about the origin by pi radians, right? So we are asked to, as usual, this R2 along with T actually defines an Rx module structure on R2, as we just saw for the general case. So how many submodules are there in R2? So what we need to find is essentially what are the invariant subspaces of this linear map, right? That's all, right?
Yes, sir.
So let's just look at T first. We know that T, since it's clockwise, okay, so for the problem, so you first write down the matrix of T in terms of the canonical basis, right? So we know that clockwise rotation by pi radians, right? That means it's cos of minus pi minus sine of minus pi. This is our usual rotation matrix, right? Sine of minus pi and cos of minus pi. Minus pi because we are taking clockwise rotations. Anti-clockwise would mean we would take plus. Alternatively, you could also see where to the basis vectors go, the canonical basis vectors go, and you could write down the matrix easily. So the point is this matrix is just cos of minus pi. What is cos of minus pi? It's minus 1, I think. Sine, this is 0, and this is minus 1, right? So this is our matrix. So we need to find out how many submodules are there in R2, that is how many invariant subspaces are there for this. Okay. Now just note what is just clockwise rotation about the origin by pi radians. You take, so any vector here, if you just join that vector, you just rotate it along, I mean, you understand, right? You sort of rotate it around the origin, right? That is what you essentially do. That is what your clockwise rotation by pi radians is. So anyways, so take any vector V. Let's say non-zero vector for the time being. V in R2. Then what is, okay. V in R2. So what is T of V? T acting on V, what is this? This is just, just note that what T is, this is minus identity, right? Minus I. So this is minus I of V, which is just minus V, right? Isn't it? So T basically maps V onto minus V. So can we not say that the subspace generated by V, or maybe yeah. So T of the subspace generated by V is already contained in the subspace generated by V, right? Because you take any vector in the subspace generated by V, it's a scalar multiple of V. So lambda times V, where lambda is in F. T acting on this will be lambda times TV, which is minus lambda V, and this is automatically in the subspace generated by V, right? Isn't it?
Yes, sir.
Thus, the subspace generated by V is an invariant subspace, and we are almost done. Invariant subspace of T for every non-zero V, or for every V, we can say, for every V in R2, right? Now finally we observe that there are infinitely many such vectors, right? I mean, they will give you different subspaces, right? Isn't it? So basically what I mean to say is, for every V in R2, and just observe that you take one V and you take another V which is linearly independent with this V, and so on, right? So all of them will give you various subspaces. So sort of it's a circle worth of vectors, right? Every point on the unit circle gives you a vector which generates a different one-dimensional subspace, right? So since how should I write this? Okay, so since v comma w in S1, so you understand what S1 is, right? Circle. Do you understand? I mean, have
Yes,
you?
sir.
Okay. So since v comma w in S1 and v not equal to w imply that the subspace generated by v, oh, there are a lot of problems here. Yeah, I should say something more. Since v comma w in S1 comma v how should I say v not equal to plus minus w implies that the subspace generated by v is not equal to the subspace generated by w. Hence there are infinitely many such invariant subspaces of T, right? Is it clear? Is it clear, Shalini?
Yes, sir.
Yeah. So we have infinitely many. Every one-dimensional subspace actually is an invariant subspace. So all of them are actually submodules, we can say. Infinitely many submodules. Submodules of V over Fx, and we are done. So I use this general construction because there are some more questions which will involve this type of problem. So yeah, so this finishes question 1, and infinitely many is the correct answer. So let's quickly move on to problem 2, and this is very easy actually. So even though it's a very significant concept about modules, so let's look at this. So suppose that M is a left R module, and you define tor of M to be all elements M in capital M such that R times M is 0 for some R in R minus 0. So you have a module over a base ring, and you define the tor of M to be equal to all elements in the module which are annihilated by some non-zero element in the ring. Okay, that is called tor M. Every such element M which is annihilated by some non-zero element of the ring, some non-zero scalar from the ring, that is when multiplied with that scalar gives you 0, such an element M in the module is called a torsion element. So that is why we have this tor notation here. So which of the following statements are correct? So tor of M is a submodule of M. So what do you think? Should this be correct? It's a subset of M, that we can clearly understand, but should it be a submodule always? It shouldn't be, right? Because there's no guarantee that it will be. For example, let us just look at this. So A is incorrect. For example, we know that every ring is a module over itself, right? The scalar multiplication is just the ring multiplication, right?
Yes, sir.
Z6. By the way, if R is a, let's say R is a commutative ring, let's say, and suppose R is a module over R, that is you consider R as a module over itself, then what do you think should the should the submodules be?
They are the additive subgroups.
Yes. No, not just additive subgroups, right? Because you also need that the subgroup should.
And closed under multiplication by ring element.
Yes. So what kind of subgroup is that? In a ring, what kind of subgroup is it which is closed under multiplication by ring elements?
They are ideals.
Exactly. So the submodules of this module will be ideals. We are taking a commutative ring, so obviously we can talk about, we are saying ideals, but let's say we took a non-commutative ring and we took a left module, then the corresponding, then a submodule will actually be a left ideal, that is closed under left multiplication by ring elements and all that. Okay. So for example, Z6 is a Z6 module. It's a module over itself, we know. Now class of 2 belongs to tor of Z6 and class of 3 belongs to tor of Z6. Why? Why do you think this is true? Because you can just take the scalar class of 3 and multiply it with class of 2, right? That gives you 0, right?
Yes, sir.
And similarly you can take the scalar 2 in the base string Z6 and multiply it with the module element class of 3. So you can multiply them and you also get 0, which implies that both the class of 2 and class of 3 are in tor of Z6. Okay, but what is class of 5? I mean class of 2 plus class of 3, this is class of 5. Is this a torsion element? Does there exist a non-zero ring element which when multiplied with this gives you 0? Is it?
No, sir.
No, right? 1 doesn't do the job, 2 doesn't do the job, 3 doesn't do the job, 4 doesn't do the job, 5 also doesn't do the job. So this is not a torsion element. So in particular tor of Z6 is not closed under addition, right? Thus tor of Z6 is not a submodule. Of Z6. So A is clearly not correct. B is even easier. So this is A. And what about B? What do you think? What should be the case for B? So if R has 0 divisors, then tor of M has to be non-zero, provided that M is non-zero. Provided that the module is non-zero, if the base string has 0 divisors, then tor of M should also be non-zero. What do you think? So let's look at this. So yeah, so since okay, so we know that R has 0 divisors, which means that there exists A comma B in R. Yeah, I should sometimes 0 is also taken to be a 0 divisor, right? So I should also add a condition that R has 0 divisors not equal to 0. That would be better. So there exists A and B in R such that A and B are both non-zero and A times B is equal to 0, let's say, right? That we know. R has 0 divisors. So also M has been taken to be non-zero. So let M be M in M such that M is non-zero. We can take this because the module itself has been taken to be non-zero. And so if B times M is 0, B is a non-zero ring element which when multiplied with M basically says that M basically gives you 0. That means that M is a torsion element in the module, right? So if B times M is equal to 0, then M is in tor M, and therefore tor M is non-zero. On the other hand, we could also have that if B times M is not equal to 0. If B times M is 0, then M is a torsion element. If B times M is non-zero, then what can we do? We can multiply A, right? So then A times B times M, which by one of the axioms of a ring action is AB times M, which is equal to 0, right? Because AB is 0 in the ring, right?
Yes, sir.
So which this further therefore implies that B times M is in tor M, right? So either M is in tor M or B times M is in tor M, and in the first case M is a non-zero torsion element, and in the second case B times M is in tor M and B times M has been taken to be non-zero, right? So it's a non-zero torsion element. The overall point of this is that thus tor of M is non-trivial, not equal to 0, and hence option B is correct. Option A is wrong, statement A is wrong, statement B is correct. Okay, let us move to the next problem. Okay, so let me first ask you. So you know what abelian groups are, but do you understand that every abelian group can be turned into a Z module? I mean, it's a Z module, right? Under a canonical action, right? Isn't it?
Yes, sir.
Yeah. So every abelian group M is naturally a Z module. So the question is saying that the action of Z, so you have, it's a Z module, so Z acts on this module M. This action of Z can actually be extended to M into a Q module. That is, sort of you can extend the action of Z to an action of Q on M. Okay, so that M actually becomes a Q module. So to be more precise, what this is saying is that, so you already have an action of Z on M. What you want to do is, so want, or it might exist or might not exist, want, or maybe let's say, does there exist? Does there exist an action of Q or a Q action, Q cross M into M, that extends the given map Z cross M to M. Q cross M, Q contains Z, so Q cross M contains Z cross M, right? So does there exist a Q action which extends the action of Z? This is what the question is. So what do you think? Will this always be true? Given any abelian group and given any abelian group which is there for a Z module, can always the action of Z be extended to a Q action on M? Is it the case always? The question is clear, right? So you have a Z module, you want to make that Z module into a Q module extending the action. So let's say alpha is in Q now, you want to define alpha times little m, right? So that if alpha is actually an integer, then that is alpha times little m is actually the original element of the Z module. Is this clear?
Yes, sir.
Yeah. So what do you think? Can any action of, I mean, can this canonical action of Z on the abelian group M always be extended to a Q action? I mean, by always I mean that for every abelian group M, can this be done? So we claim that this is not true. So we claim that this is not true. A very simple example is, consider the abelian group Z. This is a Z module, right? I mean, the abelian group structure allows you to define as Z module structure on the abelian group. So this is a Z module with action or with Z action. So Z acts on Z, right? So Z cross Z to Z. We have a mapping of Z cross Z into Z. So what does this do? This is precisely M comma N gets mapped to where? So whenever you have an abelian group, what is the canonical action of Z on that abelian group? You take any integer N, which is your scalar, and you take any group element A in the abelian group. So N dot A is precisely A added to itself N times, right? That is what your action is. So here it will be N added to itself M times. So it's just Mn. Multiplication. So the action here is precisely the ring multiplication. Okay. So this cannot be extended to an action of Q. So you can't have a mapping of Q cross Z into Z which maps every pair M comma N, where M and N are both integers onto Mn. That is, this action Z cross Z to Z cannot be extended to a Q action. Why? Because suppose there is a Q action Z which extends the z action, then there is a problem. Why? So what is the difference between q and z? We know certainly that as ring, z is contained in q. It's a subring of q, but there is something more here, right? So what is q? Q is precisely the field of fractions of z, right? Isn't it? So all non-zero elements are actually invertible in q. You sort of introduce inverses for every non-zero element, right? That is what you do when you form q, and that is actually how you construct q, right? In the foundations of mathematics, whenever you study foundations of mathematics, you first take the natural numbers in, let's say by some piano axioms or something, they are given to you, and then you construct the integers, and then you construct q from it, and the process that you do is precisely constructing the field of fractions and nothing else. So anyways, so half, we know that half times 1, so half, so suppose you have a q action, so half can act on any element of z. So half times 1 is actually an integer a, right? This is equal to a, let, or yeah, a in z, let, right? I can write this, right? Half times 1 will be an element of z because you have a q action, and then this means that 2 times half times 1 is 2 times a, right? And what is 2 times a? This is since the action extends the z action, so 2 times a is basically 2a, right? You are adding a with itself 2 times. This is only happening because the rational number 2 is actually an integer and the action extends the original z action. So 2 dot a here is just 2a, and now this is 2 times half times 1 is equal to 2a. Why can I write this? Because one of the axioms of a module and nothing else. So this implies that 1 is equal to 2a in z. A is an integer and 1 is equal to 2a. Can this be true?
No, sir.
Yeah, so this is a contradiction. So the z action on z cannot be extended to a q action. And that finishes this. So this is false. Okay. So yeah, I hope you don't have any problems or questions so far. So let's move on to the next one. So this again involves what we did in the first problem. So now take t from Rn into Rn, which is the linear left shift operator. So what does this do? It is that it basically maps any n tuple x1 up to xn onto this. So you shift everything one place to the left, right? So this x1 up to xn is mapped onto x2, x3 up to xn comma 0. This is what this operator does. You can check that this is a linear operator. It's a linear map, linear endomorphism of the vector space Rn. So the pair Rn comma t, as usual, since we have taken a linear transformation from Rn to Rn, or an endomorphism of Rn, this basically makes Rn into an Rx module, right? Just as we saw previously, it makes it into a left Rx module. So for n equal to 5, how many possible submodules are there in R5? But now we have something handy here, right? We know that the submodules of this Rx module will precisely be the invariant subspaces of T, as we observed in the first problem, right? As we did in the general case. So we can use this observation, and we just need to find out what are the invariant subspaces of T, right? Now computing this rigorously is very difficult, right? You understand why. Computing, because you are already given n equal to 5, and computing this rigorously is very difficult. So we use a trick here, okay? So we do for general n. We don't bother about n equal to 5. We just give a general answer. We do for general n. Okay. So first of all, so consider the subspace. Consider the subspaces W1, let's say W0 is equal to W0 is precisely your 0 0 n times. It's a trivial subspace. You take W1 to be equal to x1 0 0 up to 0, right? That is, there are n minus 1 zeros here. This in Rn, right? Such that x1 is in R. Okay, so all entries after the first element are 0. This is your W1. So similarly, you take W2 equal to x1 x2 0 0 0 in Rn. x1 x2 are real numbers, and you keep on doing this and you arrive ultimately at Wn, which is precisely your x1 up to xn in Rn, such that I don't need to write anything else here. So this is just Rn only, right? So what is Wn? All those tuples such that, or all those vectors such that after the nth entry everything is 0, but there is nothing there after the nth entry, right? These are n tuples, so this is precisely Rn. So you understand these subspaces, right? W0 up to Wn.
Yes, sir.
So check that each Wi is invariant under T. So already we have at least n plus 1 subspaces. Already we have at least n plus 1 invariant subspaces of T, and therefore we have at least n plus 1 submodules of T, right? I mean submodules of the Rx module Rn, right? We already have these submodules. So let us see if there are if there is anything else. Now suppose that W is an invariant subspace. Of T, okay? Then there exists some I in 1 to n, 0 to n, such that, okay, so we can say even something, I mean, let's not make it so complicated. We can just say that since Wn is Rn, so W in particular is contained in Wn, right? So we take, let I is equal to the minimum of all indexes k such that W is contained in Wk. Okay, we take I to be the minimum of all k such that W is contained in Wk. We know that if since W is an invariant subspace of T, in particular it's a subspace of T, and I mean in particular it's a subspace, so W is contained in Rn, so W is contained in Wn. Thus we can consider this set of all k such that W is contained in Wk, all k running from 0 to n such that W is actually contained in Wk. This set is non-empty and it has a least element, right, by the will ordering principle, that n is every this is the way, here we are using the will ordering principle, that is every non-empty subset of natural numbers has a least element. This set is clearly non-empty, hence it has a minimum element or a least element, right? We are calling this element to be I. So we claim that W is actually equal to Wi. We claim this, that W is actually equal to Wi. So not only is W contained in Wi, it is actually equal to Wi, where I is a minimum such k such that W is contained in Wk. Now if I is equal to 0, just look at what W0 is. W0 is just the trivial space, right? 0 just contains the 0 vector. So if I is equal to 0, then clearly W contained in Wi implies W is equal to Wi. Then W is equal to Wi, right? There's no doubt about this. W is just the 0 subspace because W is contained in the 0 subspace. So assume I is strictly greater than 0. Okay. Then we can talk about I minus 1, and since I is the minimum index such that W is contained in Wi, that means that W is not contained in Wi minus 1, right? You agree?
Yes, sir.
Yeah, so W is not contained in Wi minus 1. Thus, there exists some vector W in Wi, some vector W in Wi, some vector W in W such that W is not in Wi minus 1. So we have found some W in W such that W belongs to such that W is not in Wi minus 1, and so W is in Wi. Since W is in W and W is contained in Wi, that means that W is in Wi. Yeah. So W in Wi means that, just look at what Wi is. Wi is that subspace which consists of precisely those tuples such that everything after the ith entry is 0, right? So this means that W is equal to, it is of the form lambda 1 E1 plus lambda 2 E2 plus dot 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 plus lambda IEI, right? For some in R. What are E1 up to EI? These are just your canonical basis vectors, right? Of Rn over R. So since everything after the ith entry is 0, so I need not write about the rest of the summands, right? That is EI plus 1, EI plus 2 and so on, because the supporting scalars will all be 0 there. The coefficients will be 0, right? Since W is in Wi. Okay. Thus, so W is in Wi. So thus T, if you take some power of T, I don't know what power should we take. T applied here, T power I guess. T power I acting on W, isn't it? Yes, precisely. So T power I acting on W is lambda I E1, right? Because what is your T? Just recall, this is the shift operator. So T shifts everything one place to the left, right? So if you take T square, it will shift everything 2 places to the left and just add 2 zeros at the end, right? So if you apply Ti times, it will shift everything I places to the left, right? And add that many zeros at the end, right? Isn't it?
Yes, sir.
So ultimately, if you apply T power I on W, which is lambda 1 E1 plus lambda 2 E2 plus up to lambda I EI, you'll just get lambda I E1, because lambda I comes to the beginning and the rest of it is 0, supplied by zeros. So this is so this is lambda I EI, and since observe that W is an invariant subspace of T, we have taken W to be an invariant subspace. So T power I W also belongs to W, which implies that E1 belongs to W. Yeah, I should say something here that yes, so W is in Wi, but W is not in Wi minus 1, and that means that the scalar at the end, that is lambda I, is non-zero, right? Because if lambda I had been 0 in the expression of W, then W actually belongs to Wi minus 1, but we don't want that, right? We have taken W to be outside Wi minus 1. So the ending scalar lambda I EI, the ending scalar lambda I should be non-zero. So now we can say that lambda I E1 is in W implies that E1 is actually in W, right? So now consider, so what we want to show is that W is equal to Wi, right? Which means that we just need to show, we know that W is contained in Wi, that is by definition of I to be the minimum such element, and we just need to show W contains Wi. So we just need to show that W contains each of the basis vectors E1, E2 up to EI. So just consider the vector W minus lambda 1 E1. So this is also in W because W is a subspace. E1 is in W, so lambda 1 E1 is in W. W is in W, so their difference is in W. So what is this vector? Just look at this vector. This is just lambda 2 E2 plus lambda I EI, right? Again we do the same trick. Then t power I minus 1, right? Yes, you need to shift everything I minus 1 places. So t power I minus 1 acting on w minus lambda 1 e1. What is this? This is just lambda I e2, isn't it? Yes, am I correct? Sorry. So t power I minus 1 acting on w minus lambda 1 e1. I hope I am correct, right? Yes, everything comes to,
Yes, sir.
yeah. So this is lambda I e2, and therefore, yes, it's correct. So this is just lambda I e2, and therefore, yeah. So and therefore e2. So this also belongs to w because the vector is in w and w is an invariant subspace for t. So this belongs to w, which implies e2 is also in w. So continuing in this manner, we see that e3, e4, or maybe we can start with e1, e2, e3, ei, everything is in w, which implies that w is equal to wi. Okay, and thus we are done. That is by continuing in this way, I mean now you take w minus lambda 1 e1 minus lambda 2 e2, and then you apply some power of t to that to just observe that t is to observe that lambda I e3, this is in w. Yeah, and it goes on like this. So w is equal to wi. Thus the only submodules which in the vector space language means the invariant subspaces of T, only submodules of Rn over Rx are W0, W1 up to Wn, right? So for n equal to 5, there are 6 submodules. Is it clear? So the answer will be 6. So you have done something in general, but for n equal to 5, the answer is 6. Okay?
Yes, sir.
Okay. So perhaps this was the only sort of nice problem in the entire set. But yeah, it's good. It's a very good problem. And the rest of it is very easy, very trivial. So we just need to solve 3 more problems and they are very easy. So let's look at the next one. So you take a left R module and you call it to be a torsion module. Okay, I'll just write M here. A left R module M is called a torsion module if M is equal to tor M. So we just saw what tor M is, right? It is precisely all those elements of the module which are annihilated by some non-zero scalar, by some non-zero element of the ring. So a left R module M is called a torsion module if M is precisely equal to tor M. That is, in other words, every element is a torsion element. Every element is annihilated by some non-zero element. Yeah, by this I mean that for one element M1 there can be one non-zero scalar. For another element M2 there can be a different scalar. This is what I mean. Anyways, you understand what I am saying. So left R module M is called a torsion module if M coincides with tor M. Now which of the following are correct? So A is every finite abelian group is a torsion Z module. We know that every abelian group is a Z module. That much is okay. We just need to find out whether every finite abelian group is a torsion Z module. So what do you think? What about A? Is A correct? What is so special about finite abelian groups? Just focus on what is the Z module structure on an abelian group. You take a scalar n, you take an element in the abelian group, n times that element is precisely that element added to itself n times. So if n is positive, you add m to itself, or let's say the module element a to itself n times. If n is negative, you just add minus a to itself n times and all that. So this is your canonical structure. So is every finite abelian group a torsion Z module? In other words, for every element in the abelian group, does there exist a non-zero scalar which when scalar multiplied to this element in the abelian group gives you 0? This is easy, right? What is so special about finite abelian groups that can come handy in this context?
Finite abelian groups are cyclic.
Is that true? Is every finite?
No, sir.
Yeah,
K4 is with.
yeah. But you know something more about finite abelian groups, something very powerful there about finite abelian groups. I don't want to state the answer right away because otherwise wouldn't feel very okay because it's easy. But what is actually going on? What happens for a finite? What is so special about a finite abelian group? So you imagine the group, since we are talking about abelian groups, you imagine the group with addition. Okay, the addition is the group operation and the identity element is 0. What is so special about this? So let me just spell out the entire problem. You take a group element A. Does there exist a non-zero element in Z? Does there exist a non-zero integers n in Z such that n A, that is A added to itself n times is 0? What do you think? Why is finiteness so important here? What special do you have when you have finite groups? Okay, answer this. Suppose A is an element in your ring, I mean in your abelian group, and n times A is 0. What does that mean? N times A is 0. What does that mean?
Means A plus A and times equals to 0.
Yes, that's correct. But do you know some language for this? Some other language for this? Do we call this something, or does there exist a terminology for this? Okay, let me make it even more simple. Try to imagine everything as a multiplicative group. So n times A becomes A power n, right? A composed with itself n times. So A power n is your identity element E. What does that mean?
It means order of A divides n.
Yes, that in particular it means order of A is finite, right? A has finite order.
Yes, sir.
So is this always true for any finite group? You take any finite group, does every element have finite order?
Yes, sir.
Isn't it? This was proved using Lagrange's theorem, right?
Yes, sir.
Yes. Maybe you don't even need Lagrange's theorem for this. You can just assume A to be infinite order and take the cyclic group generated by it. That will be infinite, but the entire group is finite, which is impossible. Anyways, the point is that if you take a finite group, every element has finite order. Now take a finite abelian group with operation plus, additive operation. That means that for every element A, there will be some integer, positive integer n, such that n times A is 0. So that means every finite abelian group is a torsion Z module. So since every element, okay, so let me write it like this, that A is correct. Statement A is correct since every element of a finite group. This is true for finite groups, not just finite abelian groups. Finite group has finite order. So what about statement B now? So instead of taking finite abelian groups, we are now taking we are now concerned about infinite abelian groups, and every infinite abelian group is not a torsion Z module. So let me clarify. Maybe the statement, I mean logically it's correct, syntactically it's correct, a computer would understand this, but for us it might be a bit of confusion. Every finite abelian group is not a torsion Z module. By this I mean that you take any finite abelian, any infinite abelian group, it will not be a torsion Z module. Okay. It's not that the statement is saying that for some infinite abelian group it might not be a torsion Z module. What this is saying is, or referring to, is every infinite abelian group. So take any infinite abelian group, the statement says that that infinite abelian group cannot be a torsion Z module. In other words, there cannot exist any infinite abelian group which is actually a torsion Z module. Every infinite abelian group will not be a torsion Z module. So what do you think? You take any infinite abelian group, it can't be torsion. That is, there will exist some element which is not a torsion element, which cannot be annihilated by any non-zero integer. Is this true? Is this true? What is your intuition? What does your intuition say? So take countably infinite product. Countably infinite product, or maybe let's say, so B is correct. B is incorrect. B is not correct. Incorrect. So example is this. Take Z2 power n, which is countably infinite, product of countably infinite copies of Z. Okay. You can also think of this as Z2 power n. You can also think of this as all functions from n into Z2. That also you can think of. All functions from n into Z2. That is how you actually define products in set theory, right? Infinite products. N here is just an index set. So any function with domain n and codomain Z2, or any function that goes from n to Z2 is actually giving you an element in the product. Any mapping of n into Z2. And conversely, any element in the product is a mapping of n into Z2. Anyways, so take Z2 power n, which is Z cross and Z n times, natural number times n. So take this, and for every element is just looks like a sequence, right? For every I in n in Z2 power. First of all, this is a group you understand, right? The operation is component wise, right? And this is an abelian group, right?
Yes, sir.
Yeah. So take AI in this. What can be a particular element that annihilates this AI? What can be a particular element in integers that annihilates this AI? Sorry, I should write
0.
Z2. Yeah, I am taking countably many copies of n, not Z, n.
Yes, sir.
Yeah. So yeah, why should 0 certainly annihilates, but we are interested in seeing whether every element is
2.
yes. 2 dot ai I in n is just the 0 I in n. Right? That is the 0 tuple. For every, so this is precisely that function that maps every I onto 0. For every I, it assigns or it associates 0, 0, 0, 0, and so on. So this is certainly 0. Hence, Z2 power n is an infinite abelian group, which is a torsion Z module, because every element is a torsion element. So certainly B is incorrect, A is correct. Okay. Let's move on to the next problem quickly. So looks huge, but it actually isn't. So you are asked to, so you are again given a similar situation. You take a left R module M and you call it to be cyclic if that module M can be generated by a single element. So you have studied subgroups generated by a subset, right? Similarly, you can talk about ideals generated by a subset in a ring. Similarly, you can talk about submodules generated by a subset in a module. Okay, so a left module or a left R module M is called cyclic if there exists some element M in the module such that capital M is Rm, that is every element of capital M is some scalar multiple of little m. Okay, so we know that the cyclic Z modules in particular are precisely the cyclic groups. Okay, so now suppose that T from R2 to R2 is a linear transformation, so that as usual, since it's a linear endomorphism of R2, we know that it certainly induces an Rx module structure on R2 as we did in the beginning. Now, for which of the following linear maps T is the left Rx module R2 cyclic? R2 has a Rx module structure for any linear map T or linear endomorphism T. So, for which of the values of T or for which of these T's should this Rx module R2 be cyclic? So, option A is T is taken to be clockwise rotation about the origin by pi by 2 radians. So, you rotate everything but by pi by 2 radians, by 90 degrees in the clockwise direction. And option B is T is just your projection onto the y axis. So, xy goes to 0, y. So this, for this, I mean, there's no way of guessing or anything. There's no intuition involved. We just need to compute it. So let's see. T is, so for option A, what is T? T is cos minus pi by 2, sine minus pi by 2, sorry, minus sine minus pi by 2, sine minus pi by 2, and cos minus pi by 2. This is your T. And what is this matrix? This is just what is cos pi by 2? It's 0, right? Yeah. And this is 1, this is minus 1, this is 0. This is your T. So we just need to find out which of whether this Rx module actually is cyclic. Okay. Now just observe something. We know that R2 is a vector space over R, and we know that it has a canonical basis 1, 0 and 0, 1, right? Now, if R2 is made into an Rx module by some T, then observe that what is the action of Rx? What is the action of Rx? So you take Rx on R2, I mean Rx cross R2 into R2, you have this mapping from Rx cross R2 into R2. So what does this do? It takes fx, comma alpha, as you said, maps it onto f of t of alpha, right? So in particular, if you take a scalar c, that is a constant polynomial c, comma alpha, where does this go to? So as I said, if you take this, I mean every constant should be supplied with an identity, right? So let's say you have this operator x square, this polynomial x square minus x plus 4, then suppose this is fx, then f of t is thought of as t square minus t plus 4i, right? So that means if c is a constant polynomial, so fx equal to c, then f of t should be ci, right? So
Yes, sir.
So c acts on alpha and maps alpha to, or sends alpha to ci of alpha, which is just c alpha, right? And c alpha is just your usual scalar multiplication of alpha by the field element c. So what I want to say is that you understand that this particular action of Rx on R2 that we have via T, this action actually extends the original vector space structure, original vector space scalar multiplication. Okay.
Yes, sir.
Yes. Original R action. That is what is extended to an Rx action. So, yeah. So now we can quickly finish this. So yeah, so what I want to say is that you know that the canonical basis of R2 over R is 1, 0 and 0, 1. We can take this basis. And if we can show, if we can find some element in the module, okay, so that if you take the submodule generated by that element, or some scalar multiple of that element gives you 1 0 and some scalar multiple of that element gives you 0 1, then we know that everything is there, right? Because once you have 1 0 and 0 1 in the submodule, you can just multiply just by the scalars. You don't even need polynomials here, right? Polynomial scalars you don't need. You can just take the constant scalars and multiply them with the scalars to get everything, right? Because the Rx action is an extension of the R action. Okay, so consider the element. So we need to obtain 1 0 and 0 1. There should be some element in the module in R2, let's say AB, which some scalar multiple of AB gives you 1 0 and some scalar multiple gives you 0 1. Okay, so we consider, let's say, so yeah, so what does this do? So what does this T do? So let's see, 0 1 minus 1 0 acts on XY and gives you, or maybe AB. I don't want to confuse you with all these notations. So acts on AB to give B minus A, right? Yeah, so B minus. So let's consider 0 minus 1 comma 0. Consider this particular element. We claim that this element will generate the entire module. So consider this in R2. So you want to obtain 1 0 and 0 1. Then the scalar x times minus 1 comma 0, by our definition of the Rx action, is T acting on the vector minus 1 comma 0, right? And what is this? This is 0 comma 1, right? Because what does this do? What does T do? This maps, as we saw, A comma B onto B comma minus A, right? Isn't it? So already you see that a scalar polynomial when multiplied with minus 1 0 gives you one basis vector 0 1. And how do you obtain 1 0? How do you obtain 1 0? So just take x square dot minus 1 0 is x dot minus 1 0. That is, it's just t square acting on minus 1 0, nothing else. So we can, let's not write so much. We can just take this is to be t square acting on minus 1 0. Keep in mind that by t square I mean that t composed with t, right? There is no other canonical way, right? No other canonical operation of multiplication on the space of all endomorphisms of the vector space. So t square means t composed with t. So this is t acting on 0 1, right? Because t acting on minus 1 0 is 0 1. So what is t acting on 0 1? So a comma b goes to b comma minus a. So this is 1 0, right? Thus 1 0 and 0 1 are in the submodule, belong to the submodule. Okay, this belong to the submodule R minus 1 0. Okay, you understand the notation, right? Okay.
Yes, sir.
Oh yeah, there's a problem. Not R minus 1 0. We need polynomial scalars here. So Rx times minus 1 0. That is the submodule of R2 over Rx generated by the vector, generated by the element minus 1 comma 0. This is what I'm saying. Okay, we have written Rm here, right? For any ring R, Rm means the submodule generated by M. So here the ring is Rx, reals over Rx, real polynomials. So this is Rx times minus 1 0. So both 1 0 and minus 1 are here, and since the action extends the original R action, which implies that A comma B is also here for all A comma B in R2, right? So this means that R2 is just Rx minus 1 0. Alternatively, we could also, there's no problem with this. We could, instead of saying all this, we could say that AB can actually be generated by some scalar multiple of minus 1 0. What is this? So you just take ax square plus bx. You take this polynomial and you make it act on minus 1 0. So x square, as we saw, maps minus 1 comma 0 to 1 0. So you get a on the first coordinate plus bx of minus 1 0, which is b times 0 1, right? So you get b in the second coordinate. You add those two, you just get ab. Okay. So maybe I can just put this in a box. Okay, and then we are done. Thus for A, or maybe thus R2 is a cyclic Rx module. And similarly you can also check that option B is also correct. So I'll just write down the generator, you do the same thing, same procedure, and you check this. So B, so for option B, R2 is again a cyclic Rx module. So check that the vector 1 1 in R2 is a generator. Okay, you just need to see that every basis element is obtained as a scalar multiple of 1 1 or not. Just always be sure what you are talking about, whether you are referring to the vector space structure that is over the base field, or you are referring to the Rx module structure. Okay, so for Rx modules you are interested in subspaces, and for submodules, and for the R vector space structure you are interested in subspaces. And you know that the invariant subspaces of the linear operator T are the same as the submodules of Rx. Submodules of the module over Rx. Okay, so anyways, so both options are correct, A and B. So do you have any questions so far?
No, sir. Clear.
So, okay, so we end up with our final problem. Okay, so a left R module is called a simple module if and only if if the only submodules are the trivial module and M. So M and 0 are the only submodules. Then the left R module M is called a simple module. So it's like a simple group, right? Why do we say it's simple? Because for simple groups, what are simple groups? Those are those groups whose only what should I say?
Normal subgroups.
Normal subgroups are the trivial group and the entire
trivial
group.
one.
Yes, trivial and the entire group, right? So similarly for modules, the only submodules are 0 and M, right? That is, in other words, you cannot take a quotient to obtain something new. That is what simple means here. So left R module M is simple if the only submodules are 0 and M. So anyways, so suppose V is a finite dimensional vector space over a field K, and suppose T mapping V into V be a linear operator. Okay, so T is a mapping of V into V, or a mapping from V to V, and it's linear. So then V becomes a Kx module naturally. Again, it's obvious, we saw the construction. So which of the following are correct actually? So if the base field K is the complex number C and V is simple, then dimension of V is less than equal to 1. And if K is equal to R and V is simple, then dimension of V is less than equal to 1. So let's see. So there has to be some difference between C and R here, right? We are fully aware of what the module structure on V is. The Kx module structure on V actually is. We take help of the linear operator T for that, right? And we know that V is simple as a Kx module means that its only submodules and are 0 and V, right? But we know that the submodules of a Kx module are the same as the T invariant subspaces of V, right? Which means that the only invariant subspaces of T for the vector space V over K are 0 and V, right? T doesn't, nothing, no other subspace is invariant under the T action of the map T on V, right?
Yes, sir.
Okay, so what happens if you take K to be C? Is it the case that if K is equal to C, then dimension of V has to be less than equal to 1? So there is some difference between C and R. There is some algebraic difference between C and R. Do you know what it is? You take the field R and you take the field C. There is some difference. What is that? R is contained in C, we know that. But there is something more that we know. Have you studied the fundamental theorem of algebra ever? It's very simple. It says that every non-constant polynomial with complex coefficients has a root.
Yes, sir.
Yes.
And root equals to the degree of the polynomial.
Number of roots.
Yes, sir.
Yes, but this is not the case for R. For example, we can just take x squared plus 1 in Rx. This doesn't have any root in R, right?
Yes, sir.
Okay, so that this is the so in other words, maybe whenever you will be studying some Galois theory and field theory later on in your curriculum or training, you will see that C is something called an algebraically closed field. R isn't one, but C is. So, anyways, so so suppose so A is correct. A has to be true. Let us see why. So assume that K is C, V is simple, and assume that the dimension of V is strictly greater than 1. V has dimension strictly greater than 1. So consider, so what we want to show is that V is not simple. There is some submodule other than 0 and V. Some Kx submodule, which means that there is some T invariant subspace of V over K. So consider, so have you studied characteristic polynomials in linear algebra?
Yes, sir.
Very good. So consider the characteristic polynomial let's say fx belonging to kx. So here k is c, right? So fx belonging to cx of t, right? Consider the characteristic polynomial of t. Now fx we know is a monic polynomial of degree equal to the dimension and all that, dimension of v and all that. But the point is that it's a non-constant polynomial in cx, right?
Yes, sir.
Since fx is a non-constant polynomial, in Cx, fx has a root, right? In C. Now, what are the roots of the characteristic polynomial more popularly known as?
Eigenvalues.
Yes. Thus, T has an eigenvalue. Let's say little c with corresponding eigenvector let's say v, little v in v. Okay. Now we know that if v is an eigenvector, we can consider the corresponding eigenspace, and the eigenspace will definitely be an invariant subspace, right?
Yes, sir.
So maybe we don't even need to look at the eigenspace. We can just take the subspace generated by v. Then the subspace generated by v. Okay, I should be, yeah, I should say CV, let's say, which is the subspace generated by v. C vector space v, you take the subspace generated by the vector little v. The subspace generated by v over C. Okay, subspace generated over C by v. Yeah, generated over C by v. Yeah, so then CV is an invariant subspace. Of T of dimension 1, since dimension, so this is an invariant subspace of T of dimension 1. That means we have obtained a submodule, right? Submodule of the CX module. And since dimension of V is strictly greater than 1, hence V has a non-trivial submodule, trivial proper submodule over Cx. Thus, V is not simple, which is a contradiction, right? because we assumed V to be simple. Yeah, one thing that I should also say here is, why is a subspace generated by V, that is CV, why is this, why does this have dimension 1? Because V is an eigenvector, right? And we know that eigenvectors for an eigenvalue are taken to be non-zero vectors usually, right? I mean, yeah, I should say with corresponding non-zero eigenvector. Something is an eigenvalue means that it will have a non-zero eigenvector, isn't it?
Yes, sir.
Otherwise, every vector will be an eigenvector, or every value will be an eigenvalue, which is absurd. Yeah. So thus V is simple, which is a contradiction. I mean, V is not simple, which is a contradiction. Hence, dimension of V is less than equal to 1, and we are done with this. And what about the second one? So as I said, R is not algebraically closed, so we cannot do this, or cannot play the same trick here, right?
Yes, sir.
So we claim that B is incorrect. So B is not correct. Why? Quick answer is, take V to be equal to R2. So we know that it has dimension 2 over R, over the field R, right? And so okay, so you answered this quickly for me. So what we want is, we want to find an example where the base field is R, V is simple, and the dimension of V is strictly greater than 1. We have already taken V to be R2 over R, which has dimension 2. We just want to find or put some Rx module structure on V, that is, we want to find an operator T, or an arrow from V to V, right? That is an endomorphism of the object V, of the vector space V, such that the Rx module is actually simple. We know that the submodules of Rx, of V over Rx, are precisely the same as the invariant subspaces of T, right? And V is simple means that the only invariant subspaces of T are 0 and V, right?
Yes, sir.
So can you find an operator T from R2 to R2? So it all boils down to this, that you want to find an operator from T to R2 such, sorry, you want to find an operator T from R2 to R2 such that what? Yeah, such that it has no non-trivial proper invariant subspaces. Certainly 0 and R2 are invariant subspaces for any operator, but there are no other invariant subspaces for T. Can such a T, or can you give me an example of such a T? Just think about this geometrically. That is why I chose R2 for you. What operator is there which doesn't have any invariant subspaces other than 0 and R2? We have already considered the operator previously today.
The points by pi by 2 clockwise.
Yes, exactly. Some rotation, right? Some rotation by pi by 2, clockwise or anti-clockwise, doesn't matter. But that
Yes,
you
sir.
can check very easily yeah. So for T equal to, let's say, clockwise rotation, by pi by 2 radians, which is a morphism of R2 into R2, right? So it's an arrow from R2 to R2, it's an operator, and yeah, there are no T invariant subspaces. Thus V is a simple Rx module. Right? And yet we saw that the dimension of V over R as a vector space over R, it has dimension greater than 1. It has dimension 2, right? So certainly B is not correct. Option A is correct. Okay, and that finishes all the problems we want to discuss today, and that's all from my side. So do you have any questions?
No, sir. Thank you so much.
Okay, yeah, and thank you for joining. So see you next week. Please do attend Harish's sessions also. Okay. So bye. So let me stop the recording
Okay,
first.
sir.
Yeah.